Okay. So good afternoon, everyone, and welcome to my talk. Firstly, I want to appreciate the organizer for giving me this opportunity to give this presentation instead of Olivier Dulieu. And my name is Baara. I am a PhD student in the Institute of Quantum Optics at Leibniz University, Hannover. And our group, experimental group, is led by Professor Silke Ospelkaus. And we have a very strong collaboration with Olivier Dulieu from the theoretical group in Warsaw. So together we have made a theoretical study on photoassociation of ultracold sodium, potassium, and potassium. So let me start first with an overview. Suppose that we have a cloud of ground state potassium atoms, and inside this cloud we have diatomic sodium potassium, a few, maybe 1,000 molecules. So and they are colliding. Now, photoassociation is light-assisted collision. So if we shine a laser light with a specific frequency, there is possibility to transfer the triatomic system from collisional state to a weakly bound state. Now, the first question is, what is the significance from doing photoassociation? What is the density of weakly bound states? And is it possible to absorb a detectable signal? And how much is the photoassociation and how to calculate it? So let me first start with the significance of this study. So photoassociation of triatomic molecule is a natural extension for association of diatomic molecule. And our group has successfully created ultracold sodium potassium, bosonic sodium potassium in the absolute ground state in 2020. And the good news is that there is evidence for association of triatomic molecule using Feshbach resonances, as has been reported in the work of Young et al. In 2022. And the recent preprint paper on arXiv, the same group, they have observed a photoassociation resonances in ultracold atom molecule collisions. The second point in the significance is that photoassociation of atom molecule is a possible pathway to investigate their collisions. So as has been suggested, that atom molecule collisions are governed by a large number of resonances. And those resonances, the nature of those resonances is actually under debate, whether the long range or the short range dominate those resonances. So our approach is to build a model based totally on the long range interaction, and then we do the experiment and see if we will get a signal which is not broadened, then it means that the long range dominate the interaction. But if the signal is broadened, then that means that there is effect from the short range. Now, there have been a theoretical investigations for atom molecule photoassociation back to the 2015 in the work of Perez Rios and the recent paper from Al-Kamishishi. This is last year. So both theoretical works, they have concentrated on photoassociation with laser light red detuned from atomic transition. But our approach is to investigate photoassociation using laser light red detuned from molecular transition. This is what we will see here. So this is energy diagram. So suppose that the zero of energy, it's where we have sodium, potassium in the ground state and potassium in the ground state. Now, previous studies, as I have said, they have concentrated on the transition from S to P. But our approach is to concentrate on transition red detuned from X to P, from the singlet sigma to the triplet pi. And why we chose to do that, because we want to have a clean spectrum, which is clean from any unwanted transition, like forming diatomic potassium. So that's why we have chosen this range, which is clean enough. And on the right side, we see the triatomic molecular state using the CS symmetry group with the two irreducible representations. A prime is symmetric with respect to the mirror plane containing all three atoms, and the A double prime, which is anti-symmetric with respect to the mirror plane containing all three atoms. So our target is to go from a collisional state to reach a weakly bound state for the third doublet A prime, which correlate to the asymptote where NaK in the triplet pi and potassium in the ground state. And this is the long range photoassociation. To do that, we have first to look into the photoassociation rate in the perturbative regime. So the photoassociation rate, the number of photoassociation events per second, is proportional to the density of the sodium-potassium molecules, to the intensity of the laser, to the transition dipole moment from X to P, and to the squared of the overlap between the collisional wave function and the weakly bound wave function. So how to calculate these the wave function for the weakly bound state? To do that, we chose the coupled channels approach and the super dimer model, in which we separate the long range physics from the short range, and we focus on the long range. So supposing that we have a sodium potassium molecule which is rotating with a specific rotational quantum number, j equals 0, j equals 1, j equals 2. So and the potassium, when the potassium atom is approaching, it hinders the rotation of the sodium potassium molecule, introducing partial waves in the system. So we see that we have two angular momenta, the angular momentum small j for the atomic molecule, and the relative angular momentum small l. And those two angular momenta, they are coupled to form the total angular momentum total j. So and this is the first point. The second point, the presence of the atom will break the symmetry of the potential of the diatom. So we would have anisotropic potential, and the degree of the coupling between the various channels depend on the anisotropy of the potential. So if the anisotropy of the potential is high, then we will have a strong mixing between the various channels. So we solve the coupled channels Schrodinger equation, this is the coupled channel Schrodinger equation to get the eigenvalues and the eigenfunctions. And this term represent the matrix element, the potential matrix element. In order to calculate the potential matrix element, we have first to calculate the potential energy surface. And as we can see in this picture, the potential energy surface depends on three coordinates. We describe it in Jacobi coordinates. So small r is the bond length for the diatomic molecule. Capital R is the distance from the potassium atom to the center of mass of the diatomic molecule, and theta, which is the angle between the two coordinates. So we have calculated the potential energy surface using Jacobi coordinates with the multi-reference configuration interaction method. So here we have a two-dimensional cut through the three-dimensional potential energy surface. The vertical axis is the energy in wave number, and the two horizontal axes are the capital R down to 30 atomic units, and theta between 0 and 180 degrees. Now, after we have the potential energy surface, we calculated, we solved the coupled channel Schrodinger equation, we get the eigenvalues. So those eigenvalues, they are in two categories: bound levels, which are below small j equals 0. So we have solved that for total angular momentum j equals 1. So those bound levels, those eigenvalues, which are below j equals 0, they are bound levels. And those eigenvalues between j equals 0 and j equals 1, they are pre-dissociation resonances. So after we have those, we can get the photoassociation rate, as I have described previously. So in our, under the experimental conditions in our lab, at 200 nanokelvin with the density of sodium potassium 10 to the power 11 per cubic centimeter and laser intensity of 100 watt per centimeter square, we have here the photoassociation rate, the number of photoassociation events per second as a function of the red detuning from NaK in the triplet by V equals 0, J equals 1, plus K. So we have the bound state and the pre-dissociation resonance between J equals 0, J equals 1. So since the photoassociation rate is at most larger than the decay rate, that means the photoassociation rate is faster than the decaying rate, which indicates that it's possible to observe photoassociation detectable signal. So I don't have so much time, so I will just thank you for your attention.
Great, so we have a few minutes for some questions.
Yeah, I can have a question.
Yes, please.
So did you calculate the widths of the pre-dissociating states? So can you access them? Do you have like, because if the widths would be...
Yeah, will be the next step to calculate this width.
Because I would expect that the lifetime can be very short and the widths can be comparable to this energy. Overlapping, you don't see.
Yeah. So in this way, we can focus only on the resonances which are below J equals 0. Yes, please.
The MACR used all of the electrons of the molecules. How many?
1 electron valence. So the system consists of 3 valence electrons.
Okay. Yeah, makes sense. Yeah.
Yeah. So the computation is not really so expensive. Yeah.
Okay, I think that's perfect timing. So
thank you very much.